In this video, we're going to do a ton of examples, all just doing integrals with trig functions. We learned about integration by parts in our last video, but sometimes integration by parts isn't enough to do problems either. So I hope you remember all of your trig identities because we're going to be using quite a few of them on this particular video. We're just going to start right away with an example. Let's evaluate the integral of cosine to the third of x dx. Now, I know from experience that a lot of students are wanting this to be a sine to the fourth over 4 because they're thinking antiderivative of cosine is sine and do a power rule with it. That doesn't work. If you actually take the derivative of that, you're definitely not going to get cosine to the third because you'd have to use a chain rule to do that derivative. Now, you could think, hey, let's do u substitution, u equals cosine. So I'd have a u to the third. That's great, except that du would then involve a negative sign, and I don't have a negative sign here to use. You could also try integration by parts, but that doesn't work on this one either. If you don't believe me, go ahead and try it. So what are we going to do instead? We're going to use algebra and trigonometry. So the first thing that I know is that cosine to the third is the same thing as cosine squared times cosine. That's just algebra. And now I do know a trig identity for cosine squared, and you all should as well. We know sine squared plus cosine squared is 1. So cosine squared is equal to 1 minus sine squared. Using that trig identity, I get 1 minus sine squared of x times cosine of x dx. And now at first glance, this integral looks more complicated than what we had to begin with, but it's not, because this integral we can do with u substitution. If I let u equal sine of x, I would get a 1 minus u squared here. My du would involve a cosine of x, and I have a cosine in the problem, so it should work out just fine. So let's go ahead and write down our substitution. So if I let u equal sine of x, then du is going to be cosine of x dx, which means that du divided by cosine of x is going to be dx. So now if I go ahead and rewrite my integral using the substitution, I'm going to have a 1 minus a u squared. We had a cosine x, and my dx is du over cosine x. And you can see that those cosine x's cancel out. So I can rewrite my integral as just a 1 minus u squared du. Now this guy we can do just by using our power rule. So even though the integral was complicated at the beginning, using a trig identity allowed us to just rewrite it using our u substitution. So the antiderivative of this, we get a u minus a 1/3 u to the third. And then I just have to plug my u back in. And I get sine of x minus 1/3 sine to the third power plus our constant as my antiderivative. All right, so that wasn't too bad, but luckily that one used our favorite trig identity. Sine squared plus cosine squared is 1. Sometimes we're going to need some of our other trig identities though, so it's very good to make sure you refresh yourself on your trig identities. Let's do another example. Let's do an integral of sine to the fifth times cosine squared dx. Now I'm going to use kind of the same trick I did in the last one. I can rewrite this sine to the fifth as sine to the fourth times sine. So I have a sine to the fourth, a sine, and a cosine squared. And now this sine to the fourth, that's the same thing as sine squared squared. So I can write this as sine squared of x squared sine of x cosine squared of x dx. And now I'll fully admit this looks terrible right now, but we're going to still use that same trig identity we used from the last problem and get this to look correct. We have a choice. I can either change this sine squared into 1 minus cosine squared, or I can turn this cosine squared into 1 minus sine squared. Now, one of those is by far the better choice. If I turned this cosine squared into sine squareds, then everything in my whole problem has sines in it. So if I chose u equals sine, my du would involve a cosine, and I wouldn't even have a cosine anymore in the problem. That's an issue. But if I turn this sine squared into stuff involving cosine, I could do u equals cosine, and my du would involve a negative sign, and I'd still have this sign here to end up canceling out when I do my du. So that's the way we're going to want to do it. Turn this sine squared into 1 minus cosine squared. Everything else stays how it was. And now it's all set for substitution. I can do u equals cosine of x. So if I let u equal cosine x, that means that du will be negative sine dx, and that means that dx is du over negative sine of x. Rewriting my integral using this substitution, I have an integral of 1 minus u squared squared. I have my sine of x. I have another u squared, and I have du over a negative sine x. Sine x's cancel out, and that negative can come in the front. So this gives me negative integral 1 minus u squared squared times u squared du. And now I just have to do some algebra. I can distribute this 1 minus u squared squared, and then distribute my other u squared into that, and then we'll be ready to just use a power rule. So let me do a bunch of distribution. We get a negative 1 minus 2u squared plus u to the fourth times a u squared du. And now distribute that u squared to get negative integral of u squared minus 2u to the fourth plus u to the sixth du. And now we're ready to use our power rule. Using the power rule, I'm going to get negative. I have 1/3 u to the third, a minus 2/5 u to the fifth, and a plus 1/7 u to the seventh, plus our c. Now be careful, I had that negative on the outside. I chose to do this by leaving the negative on the outside and putting a set of parentheses. That's just to make sure that I remember to subtract all of these things. So now I'm going to distribute that negative, which changes all of my signs. And then all I have to do to finish the problem up is plug my u back in. U is equal to the cosine of x. So my final answer is that I get negative 1/3 cosine to the third of x plus 2/5 cosine to the fifth of x minus 1/7 cosine to the seventh of x plus a constant. And that is the answer to the original problem. All right, so now you're seeing how these trig identities that you learned way back in trigonometry class can help you with some pretty complicated integrals. Makes it so that we're actually able to calculate them. Let's do another example where we have to use a different trig identity, because it's not always going to be sine squared plus cosine squared is 1. This time, let's find the integral from 0 to pi of sine squared x dx. Now, right away, you're probably thinking, well, sine squared is 1 minus cosine squared. And that's great, except we don't know how to integrate that either. We would need to do a substitution, and that means we would need a sine and a cosine to do that substitution. That doesn't work. But there is another trig identity that we can use that uses that sine squared. Here's a refresher of some half-angle identities. Both of these come up quite a bit. Sine squared of x is equal to 1/2 times 1 minus cosine of 2x. And cosine squared of x is equal to 1/2 1 plus cosine of 2x. Both of these show up quite a bit in doing trig integrals. And of course, on this particular problem, I need this first half-angle identity. I can rewrite my sine squared of x as 1/2 times 1 minus cosine of 2x. So let's do that. Rewriting using this identity, I get that my integral is the integral from 0 to pi of 1/2 times 1 minus cosine of 2x dx. And now I can get ready to integrate this by kicking the 1/2 to the outside, and then I can use some substitution. So 1/2 integral from 0 to pi, 1 minus cosine of 2x dx. Now I do need a little bit of substitution because we do not know the antiderivative of cosine of 2x. We know an antiderivative of cosine of x. So I just have to do a little baby u substitution of u equals 2x, which means du is 2 dx. This means du over 2 is dx, and we're also going to change our bounds. X equals 0 means my u is 2 times 0, which is 0. And x equals pi means that u is 2 times pi, so 2 pi. Rewriting this integral with these new bounds and my new variable u, I'm going to have a 1/2 integral from 0 to 2 pi of 1 minus cosine of u, and my dx is du over 2. So this 1/2 on my du, I can kick to the outside. So now I'm going to have a 1/4 in front of my integral. 1/4 integral from 0 to 2 pi, 1 minus cosine of u du. And now this we can do just with our standard antiderivative rules. I get my 1/4. Antiderivative of 1 will be u. Antiderivative of a minus cosine is going to get me a minus sine of u. Then I just have to plug in my 2 pi and plug in my 0. When I plug in 2 pi, I get 2 pi minus sine of 2 pi, multiplied by that 1/4. And then I have to subtract what I get when I plug in the 0. So I get a minus 1/4, 0 minus sine of 0. And now we just have to remember all of the things on our unit circle. Sine of 2 pi is 0. Sine of 0 is 0. So all that I have left from this is the 1/4 times the 2 pi. Which of course is just pi over 2. That's my final answer. So that one wasn't too bad. That was using a half angle identity. So you might expect to use the sine squared plus cosine squared as 1, and you might expect to use one of those half angle identities. Sine squared of x equals 1/2 times 1 minus cosine of 2x. And cosine squared of x is 1/2 times 1 plus cosine of 2x. Let's do another example. The integral of sine to the 4th of x dx. Well, I know that sine to the 4th is sine squared squared. So I'm going to start by writing it that way. Now, just like the last problem, we're not going to want to write this as a 1 minus cosine squared, because then I don't have any signs left in the problem and it makes use substitution impossible. But I can use one of those half angle identities instead. So using one of the half angle identities, I get my sine squared is equal to 1/2 1 minus cosine of 2x. And then all of this is squared. Now that looks a little disgusting, but it's going to be okay. So what I can do here, first notice that this 1/2 is going to be squared, so that'll be a 1/4. And I'll pull that 1/4 to the outside. Then I just have to square 1 minus cosine of 2x. And I can square that by distributing. So let's go ahead and distribute. So I have a 1/4 times the integral of 1 minus 2 cosine of 2x plus a cosine squared of 2x dx. Now most of this is okay and ready to go. I can do an antiderivative of 1. I can do an antiderivative of this minus 2 cosine of 2x if I just do a little u substitution. U equals 2x like we did before. But this guy, cosine squared, I can't do that one yet. We're going to need another trig identity. And I would use our other half angle identity. So I can replace that cosine squared with the other half angle identity, which is 1/2 1 plus a cosine. And we just have to figure out what goes in the parentheses. Now, the identity says that cosine squared of x is equal to 1/2 times 1 plus cosine of 2x. But I didn't have just an x in my cosine squared, I had a 2x. I have to double it when using this identity. So I'm going to have a 4x after using that identity. Now I would go ahead and distribute that 1/2. And so now my integral is equal to 1/4 times the integral, 1 minus 2 cosine of 2x, plus 1/2, plus 1/2 cosine of 4x, dx. And I can combine my 1 and my 1/2 together to be 3/2 minus 2 cosine of 2x and plus 1/2 cosine of 4x dx. And now we're ready to do the antiderivative. Now, some of you might need to write out the u substitution explicitly. Others of you might have figured out the little trick. When I have 2x in here, I end up having to divide by a 2 when I do my u substitution. Same with this guy. If I did u equals 4x, I would end up having to divide by 4. So I'm going to go ahead and integrate this one without writing out the u substitution explicitly. But if you need to write it out, feel free to pause it, write it out, and you should get to the same result. Antiderivative of 3/2 is 3/2 x. Antiderivative of a cosine is going to be sine. And then I'm going to have a sine of 2x, but I have to divide by 2 using that little mini u substitution. So it's going to cancel out that other 2. Now I have this 1/2. I'm going to have a sine of 4x, but I have to divide it by 4 using, again, that little u substitution. Simplifying this so it looks a little more normal. I have a 3/2 x minus a sine of 2x plus a 1/8 sine of 4x plus my c. And all of that is still multiplied by 1/4. You can leave your answer just like this if you like, or you could distribute that 1/4 if you wanted to. If you distribute the 1/4, you will get 3/8 x minus 1/4 sine of 2x plus 1/32 sine of 4x plus c. So that one had to use 2 different trig identities. Sometimes you need more than one in the problem, and sometimes you don't. So we should get some more practicing with this, because I know trig identities are usually something that people don't really remember all that well. So let's do one where we use yet another type of trig identity. So far we've used the sine squared plus cosine squared as 1. That's a Pythagorean identity. And we've used some of our half angle identities. And now let's do this one. Let's evaluate the integral of tangent to the 6th of x times secant to the 4th of x dx. And I'm just going to remind us of a trig identity that uses secants and tangents. We have secant squared is equal to 1 plus tangent squared. So that's the identity we're eventually going to be using on this problem. Now, how do I want to write this? Well, we need to remember that when we're doing these sort of trig identity problems, we're probably going to end up doing u substitution at some point. Now, if I had u equals tangent, I would need a secant squared to serve as my du. If I did u equals secant, well, then my du would have to be a secant times the tangent. Now, I notice that I have tangent to the 6th, secant to the 4th. Secant to the 4th is secant squared squared, or you can think of it as secant squared times secant squared. I can turn one of those secant squareds into 1 plus tangent squared, and I can leave the other secant squared alone to serve as my du. So let's do that. I can have tangent to the 6th, secant squared, and secant squared dx. And I'm going to turn that secant squared in the middle into 1 plus tangent squared. Because now I can do u equals tangent of x. My du would be equal to secant squared of x dx. So if u is tangent, then du is secant squared x dx. And just because I've been doing it this way, I will show that dx is equal to du divided by secant squared. So now when I rewrite my integral with the substitution, we get u to the 6th times 1 plus u squared. There's my secant squared of x, and dx is du over secant squared x. And my secant squareds get to cancel out. So what I have left is an integral of u to the 6th times 1 plus u squared du. Now I can distribute, and then we can just use our power rule. So when I distribute, we get an integral of u to the 6th plus u to the 8th du. Now we're all set for our power rule, and then we just have to plug our u back in. The power rule gives us 1/7 u to the 7th plus 1/9 u to the 9th plus c. And then when I just plug my tangent of x back in, I get 1/7 tangent to the 7th of x plus 1/9 tangent to the 9th of x plus c as my answer. All right, so that one wasn't too bad either, as long as you know your trig identity. If you don't know the trig identity, you end up getting a little bit stuck. Let's do another one involving tangents and secants. The integral of tangent to the 5th of theta times secant to the 7th of theta d theta. Now, I'm going to use that same trig identity from last time, but I'm going to go about it a little bit different this time. So on the last one, we had even powers of tangent and secant. And so I just separated off a secant squared to serve as my du and did a u equals tangent. This time I have odd powers of tangent and secant. And I know that if u is equal to secant, then my du involves secant times tangent. So I'm going to separate off one secant and one tangent, kind of push it to the side. When I do that, I'm going to just rewrite the integral as tangent to the 4th times secant to the 6th times my other secant and my other tangent. So first notice that this is the same exact integral. I just pulled one of my secants and one of my tangents off to the side. And now I can rewrite my tangent to the 4th in terms of secants. First, notice that tangent to the 4th is the same thing as tangent squared squared. And nothing else is changing in this integral. And now using that same trig identity from the last one, where I did that, I already forgot. Secant squared is 1 plus tangent squared. Well, then tangent squared is going to be secant squared minus 1. So I get a secant squared minus 1 squared times a secant to the 6th times a secant of theta and a tangent of theta d theta. Now I'm ready to do some substitution. If I let u equal secant of theta, then du is secant theta, tangent theta, d theta. And that means that my d theta is going to be equal to du over secant times tangent. So now let me rewrite my integral using this substitution. I would get u squared minus 1 squared times u to the 6th. Be careful, don't write this one as u. Keep that as secant theta, tangent theta, because my d theta ends up being du over secant theta, tangent theta, and then those guys get to cancel out. So now I get an integral of u squared minus 1 squared times u to the 6th du. Go ahead and distribute all of that, and I get an integral of u to the 4th minus 2u squared plus 1 times u to the 6th du. And now I can distribute that u to the 6th through to give me an integral of u to the 10th minus 2u to the 8th plus u to the 6th du. And now it's just power rule and plugging your u back in at the very end. Power rule gives me 1 over 11th times u to the 11th minus 2/9 u to the 9th plus 1/7 u to the 7th plus c. And now we just have to plug our secant back into the problem. And then that is my final answer. So that one, again, wasn't too terrible as long as you use your trig identity and make sure you play with the problem appropriately so that the u substitution works out. Remember, your goal is so that when you plug your dx or d theta, when you plug that in so that it's a du over something, you want your other stuff to cancel out. That's what we're trying to have happen. Now, sometimes when we're doing all of these trig integrals, we're actually going to need 2 other formulas. One of them you should have learned already in Calc 1. The integral of tangent is equal to the natural log of the absolute value of secant. And another formula that you might not know is that the integral of just secant is natural log of absolute value of secant plus tangent plus c. These 2 formulas come up quite a bit in these problems, so it's good to just memorize them. And we're going to actually do one example where we use each of these. So let's find the integral of tangent to the 3rd. Well, first thing I notice with tangent to the 3rd is it's the same thing as tangent times a tangent squared. And what tangent squared is equal to, using one of my trig identities, tangent squared is secant squared minus 1. And now I can distribute this and rewrite it as 2 integrals. I'm going to have an integral of tangent x times secant squared x minus an integral of tangent x. So I just split it up into 2 integrals. This second integral over here is one of those formulas that I just wrote down. The integral of tangent is equal to the natural log of the absolute value of secant of x. And for this guy, I can just do u equals tangent, because then du takes care of that secant squared. So for the first integral only, we're going to do u is tangent. So du is secant squared, which means dx is du over secant squared. So I can now rewrite my first integral using u's. I'll have a u secant squared of x du over secant squared of x, and I still have this other integral tangent x dx. Remember that one we have a formula for, so I'm not using substitution on that integral. So now this first integral is just integral of u du. My second integral, I'm just going to go ahead and take that antiderivative using that formula. Natural log of secant x and a plus c. Now for this integral of u du, that's a power rule. And then you just plug your u back in. So I get a 1/2 u squared, and I still have my minus natural log absolute value of secant x. Plug the u back in, and then we're finished. All right, so that one used a trig identity, one of our special formulas, and use substitution. As you can see, sometimes we're going to have to use multiple techniques in the same problem. Now, something that hasn't come up in this video is integration by parts, which we learned in our last video. Does that mean that we're never going to need integration by parts when we have all of these crazy trig identity integrals? Of course not. We're going to need that. In fact, my next example, let's just do one with integration by parts. You can expect all of the different things to happen, even in the same problem. Some of these problems can get pretty involved. So for our last example of this video, let's do the integral of secant to the third. And I'm going to do this with integration by parts. So first I'm going to write this as secant times secant squared dx. Now you might be thinking, well, why don't I just turn this secant squared into something involving tangent squareds? Well, because then if I did u equals tangent, the du would have to be a secant squared, and I only have one secant left. So that would not work. So we're not going to use that trig identity on this problem. Instead, we're going to do integration by parts. We need to pick a u and a dv. Now, I personally would pick my dv to be secant squared, because I know the antiderivative of secant squared is tangent. If I had done u equals secant squared, you would need a chain rule to find du, and that gets more complicated. But if u is just secant, okay, the du is a little more complicated, but at least it didn't involve a chain rule. My du would be secant x times tangent x dx. Now my dv is secant squared, so my v would just be tangent. Using my integration by parts formula, remember that your integral is going to be equal to u times v minus the integral of v du. So my u times v is secant x tangent x minus the integral of v du. Well, v times du, I'm going to have a secant, and I'm going to have a tangent squared dx. All right, so now what do we do with that? Now I'm going to end up using one of my trig identities. So first, let me rewrite what I have up here. We had secant x tangent x minus an integral of secant x tangent squared of x dx. And I'm going to use a trig identity to rewrite that tangent squared. My tangent squared is equal to, let's see, that would be a secant squared minus 1. So now let me go ahead and distribute. So I get secant x tangent x minus an integral of secant cubed x. And then I'm going to have a plus an integral of secant x dx. So take a second to look at this. The integral of secant x dx we have a formula for. And in the middle here I have a negative integral of secant cubed x dx. That was our original problem. Remember that one example in the integration by parts video where we had to add that integral to the other side and then divide by a constant? That's what's going to happen on this one. So let's go ahead and just simplify this integral with the formula that we have. I'm going to have secant x tan x minus my integral of secant to the third. And then this guy, antiderivative of secant, is natural log of absolute value of secant x plus tangent x plus your constant. So now I'm going to, let's just rewrite the entire problem where we are, because now it's just algebra to finish it up. So what we have at this point is the integral of secant cubed is equal to secant x tangent x minus an integral of secant cubed plus a natural log of absolute value of secant x plus tangent x plus a constant. So now I can solve this by adding this secant cubed in the integral to the other side. When I add that entire integral to the other side of the equation, I get 2 times my integral of secant cubed x dx equals everything else I had. Secant x tangent x plus a natural log of absolute value of secant x plus tangent x plus our constant. And that means that the answer to my original integral of secant cubed, I can get by just multiplying both sides by 1/2. And I get 1/2 times secant x tangent x plus natural log of absolute value of secant x plus tangent x and plus a constant at the very end. Now, wasn't that problem pretty satisfying? You probably are thinking not so much. You don't really like that problem very much. I like this problem because this problem shows you how we can do some really, really complicated integrals now, just by using our integration by parts, sometimes substitution, sometimes trig identities. And now you're getting into the real meat of Calc 2. What makes Calc 2 so hard to learn? It's the fact that we have so many different techniques and you don't always know what to try. So you just have to try to build the instinct up. I'll try to give you as much advice as I have on how to choose. But a lot of times you're going to choose a technique and it's not going to work. And the important thing is to not get discouraged and instead try a different technique until you build your instinct up. If you have any questions, you can feel free to drop them below. Or if you're a current student of mine, feel free to email or ask in office hours. And I'll see you guys next time when instead of having problems with trig already in them, we get to introduce trigonometry to the problem to make our lives easier, believe it or not. So come back for that one next week, and I'll see you guys next time.